Hey, Alex, Miss Johnson. Today's video is going to talk about using limits to talk about the end behavior or the horizontal asymptotes for functions. I'm going to kind of use the classic functions that we like to talk about a lot in math class in high school to talk about this, but this applies to anything, right? Any function. Okay, so when I write the limit as x approaches infinity of f of x, this means, like in English, oh, should I type it? Let's be bad. Let's type it. Um, this means what is happening to the like very right of the graph, right? Um, or it's just talking about like as you go off to infinity, positive infinity, positive infinity. What is the function doing? Right. And similarly, as you would expect for the limit as x approaches negative infinity, it is the same, except it is the very left of the graph, and it is negative infinity. So we're gonna quick hot patch that in right now. Very left and negative infinity. Okay, let's do some examples of this notation. So if I say, what is the limit as x approaches infinity of x squared, and what is the limit as x approaches negative infinity of x squared? We're looking at this parent quadratic function. All right. As we approach infinity, I've been doing this instead and I like it better. Let's do that. As we approach positive infinity, that's just basically me like tracing the function all the way to the right forever. This we would say it does not exist because it's going off to infinity. Right? Actually, same for negative infinity. As we trace it all the way left, it's going off to positive infinity. All right. Let's copy and paste these. No. Different color, different graph. Let's do the exponential function. When we're going off to positive infinity, what's the limit of e to the power of x as x approaches infinity? That's the positive direction. We're just going to the right. What's the end behavior to the right? It's infinity, which technically does not exist, right? This one's more interesting to me. Y'all can decide how you feel about math. What's the limit as x approaches negative infinity of e to the x? This is saying as we go further and further left, as we plug in more and more negative numbers, as we plug in negative 1,000, negative 1,000,000, negative 1,000,000,000, what are we getting closer to? It's not going off to negative infinity, right? It doesn't get infinitely negative. It's getting closer to 0. So this limit actually does exist and equals 0. So we would imagine that for the rational function for 1 divided by x, both the limit to positive and negative infinity are both getting closer to 0. We can see for the linear function, the limit as x approaches infinity goes off to infinity. But for negative infinity, it's getting closer to negative infinity, right? I think one of the wackier, wilder ones is sine. The are just gonna let me do that. The limit as x approaches infinity or negative infinity of sine, we don't just get to draw an arrow and say, oh, it was pointing up, or like, oh, it was pointing down. What's really happening is that it's bouncing forever, right? And so it doesn't really get closer to 0 or negative 1 or 1 because it's constantly bouncing and oscillating between the two. So this straight does not exist because it's constantly bouncing. It's not getting closer to any one thing. because it's not, right? This also does not exist. And then the other wacky wild one I want to talk about is the logarithmic function. For ln of x, good in print as well. As x approaches infinity, you're actually just going to infinity, right? So this does not exist because it's going off to a non-finite number. This one doesn't exist in a wacky way because you're actually not allowed to plug in negative numbers to the logarithmic functions. I don't know if you remember that. We're like, this does not exist, right? You're not allowed to plug in negative numbers to logs. So the limit as x approaches negative infinity for log of x doesn't exist because you're simply not allowed to plug in these numbers. And that's kind of what the end behavior using limits is like. The horizontal asymptotes is like on the exponential function where we draw in these things. We're saying, oh, it's getting closer to 0. Or on the rational function, we say, oh, it's getting closer to 0, right? So we can imagine if I told you, all right, mystery function, f of x, but you know these two things about it. You know that the limit as it approaches infinity is 0. And you know the limit as it approaches negative infinity is, I don't know, 2, right? If I wanted to graph this, I would say, okay, there's definitely a horizontal asymptote at 0 and one at negative 2. So maybe our function looks like getting closer to 0, getting closer to 2. It seems fine to me. If we have a function where we told, okay, we've got a mystery function, it's called g, but we know these two things about it. We know as the limit as x approaches infinity of g of x, it doesn't exist because it's going close to infinity. And the limit of x approaches negative infinity of g of x doesn't exist because it's approaching negative infinity. What could that look like? There's a lot of options here. Boom. It's a straight line. That works, right? As we go further left, it's going up. As we go further right, it's going up. Left, it's going down. We could also have this one, right? There's a lot of different functions that would work here. As long as the end behavior to the right is going to positive infinity, aka what this is saying, and to the left is going to negative infinity, aka what this is saying. All right, guys. My sign off is, as always, if you're stressed about calculus, oh my gosh, you should not be. Email me. Make some office hour appointments. I will talk you down and talk you through it. All right, guys. Bye.